but my name is Johnson Duong. I'm a mechanical engineering student, and alongside with me is Matthew Dutaud, who is a chemical engineering student. And today we're going to be talking to you about the lifecycle testing of an ARMCHAIR. So the goal of this project was to showcase to students the interplay between design, analysis, and testing. And lifecycle testing involves gathering large amounts of data, filtering out the ones that matter, and then forming a realistic testing system. So with this project, we're constantly going through a cycle of design, analysis, and testing. And over the next couple of slides, we're going to show you exactly how this project follows this process. When we first started this project, we needed to figure out a way to design an instrumented machine that can conduct fatigue testing on the chair. And by instrumented, we mean basically rigging up the testing machine with sensors and cameras to collect data about the amount of force that's applied into the system and the amount of deflection that would occur in the chair when we're sitting in it. And the goal of this machine is to simulate as closely and as realistically as possible a person sitting in the chair. And to define fatigue testing, that basically just means applying a load to a certain object over a given period of time in order to analyze when exactly the chair or the object would break or fail. But before we actually get started on making the machine itself, we need to take a step into the finite element analysis side of things. So this is essentially just modeling a digital version of the chair on our computers, and then the computer would do the calculations to show us exactly the stress behavior the chair would experience based on loads that would be applied to it. And using this, we can then validate these results by physically performing the experiment and observing and analyzing the stress and deflection of the chair while it's actually being used. So I'll hand it off over to Matthew to get more into the specifics of the finite element analysis.
Thanks, Johnson. So now I will talk a little bit about the importance of a digital twin in this project. There are three main inputs to the design process for this project. First, we have the geometry of the design. Second, the loading conditions that the design will experience. And third, the material of the design. And any number or combination of these inputs may be changed at each iteration of the design cycle as the design continually improves. So more specifically, the design cycle of this project is as follows. First, a significant amount of data is collected for a wide variety of loading conditions in a realistic environment, and this is typically a very lengthy process. Next, all of these loading conditions are simulated in ANSYS AIM through finite element analysis, allowing us to determine the small subset of the conditions that would actually cause damage to the chair over its lifetime. And once this subset has been identified, these conditions are replicated many times to simulate the life of the chair and determine the modes of failure, specifically what parts of the chair will fail and after how many cycles. This information is then used to improve the design, whether that be updating the geometry of the chair or the material that will be used in the manufacturing. Now, the presence of a digital twin allows us to eliminate the data collection stage entirely after the first iteration, as the updated parameters of the simply input into the model and the simulations can begin to run again. This will significantly increase the speed of the design cycle and allows for the process to become automated. And as with any digital simulation, the results must be validated, and we will be doing this with the instrumentation that is shown on the following slide.
So on the left, we have a picture of this CAD model, so the computer-aided design model of the actual chair and the chair testing machine alongside it. So like I mentioned before, the goal of the machine is to simulate as closely as possible a person sitting in the chair seat and to model this deflection. And the way this works is the linear actuator, which I'm pointing to with the cursor on my screen, introduces a force of 200 pounds of force into the system, which is then transferred over to this bell crank. And what the bell crank does is convert the horizontal force into a vertical force. And when that vertical force is converted, then it pulls down this load arm through the linkage arm that I'm pointing to on my cursor as well. And once that load arm pulls down, it also brings alongside with it the seat of the chair. So this models exactly what we want, a person sitting in the chair itself. And now on the right over here, we actually have a picture of the process that we've had of the progress that we've had so far with making the chair testing machine. It's not complete, but it's definitely getting there. And I would also like to mention, with a typical chair, you probably wouldn't see it fail into maybe like 40 years after its usage, if you're assuming that you're using it normally. But with fatigue testing and with this machine, we want to try to speed up this process and automate it. We definitely don't have time 40 years of time to do the testing on the chair itself. So by using this machine, we can effectively reduce that time into just a matter of weeks, for instance, and actually see what forces would cause the breakage in the chair itself.
So there are many different aspects of engineering that come into play in this project, in all of the design, analysis, and testing segments. Portions of this initiative can be used to develop a wide range of meaningful and engaging projects for students across different engineering disciplines. For example, we are currently working on developing a material selection project to be run in a materials course, in which students will use simulation results from the finite element analysis, as well as predefined product constraints such as weather resistance or durability, to screen a database of 4,000 plus materials down to maybe 3 or 5 viable materials that could be used in a final design. Now, while we have been talking about the life cycle testing of a chair, this geometry may not be very exciting or engaging for some of the students, and thus we have also been developing a project that centers around a more complicated, engaging, and interactive geometry, and that is a bicycle frame.
Thank you, Matthew. My name is Mizzen, and I'm currently in civil engineering, and I've been working alongside Johnson in our project, which is life cycle testing of a bicycle. The purpose of this project was to design the geometry of a bicycle frame by utilizing online resources to learn as much as we possibly could about the design of bicycles and all the parts that are included in the manufacturing of a bicycle. However, to build a bicycle frame, we would need a jig to hold our frame in place so that it could be welded together. So we had to design a jig with maneuverability to fit bicycle frames with different geometries, which I will get into later. To ensure that we did not waste our time manufacturing a bicycle frame that would fall apart the first time we wrote it, we tested it to validate the safety of the bicycle through computational analysis so we could then perform physical stress testing on the frame once the time came. To conclude the process of going through the design, manufacturing, and testing of a bicycle, we wanted to elevate this process by creating an automated custom bike geometry generator so that anyone could build a bicycle frame by inputting their geometry, and a bicycle would automatically be designed and generated to fit them. Here we have a picture of the 3D model of our frame that was developed in SOLIDWORKS. The design of this bicycle frame was intended to be versatile so that it's comfortable, has adequate performance, and can be ridden on a wide variety of terrain. This was done by carefully selecting the proper angles for our tubes. As well, we ensured this bike would fit myself and Johnson despite our height differences by ensuring the length and height of our tubes were adequate, so that neither of us would be reaching too far or be hitting the ground while riding the bicycle. To hold our frame in place while it is welded, we have our jig, which can be seen in the picture on the right. Our frame is also in the picture and is attached to the jig to demonstrate how the frame will be held on the jig when the time comes to weld the frame. The arrows in this photo demonstrate the adjustability of our jig so that we can fit a wide variety of bicycle frame designs. And the photo on the left is a picture of our tubes that came in yesterday. We are planning to cut these next week and place them on the jig to be welded once we finish machining and assembling the jig.
So this is where the life cycle testing part of things comes into play. Like Connor mentioned before, we want to make sure that this bike frame doesn't fall apart when we're riding it, because that can possibly lead to people injuring themselves or breaking a few bones, and we definitely don't want that. Similar to the chair testing project, we also want to do some sort of fatigue testing on this. But first, we got to do a finite element analysis of the frame. So with a chair is a static object, and the loading conditions on it are quite honestly fairly boring, because most of the time the loading conditions it would just be simply someone sitting in the chair. But with a bike, it's a dynamic object. It's going to be subjected to much more complex and complicated loading conditions. And some of these we try to model as realistically and as accurately as possible in our finite element model. And some of these loading conditions include riding the bike normally, if the front wheel were to hit a wall, riding while standing on the pedals, and abrupt front and rear braking in cases of like an emergency, for instance. So just to reiterate, the frame finite element model is just focused on just seeing how the stress behavior would result in the frame itself, and we're not necessarily worried about the FEA and like the wheels and fork, for instance, which would just be holding the front wheels. And on the right over here, animation of the finite element model, particularly for the loading condition where a front wheel would be hitting a wall. So any colors that you see that are closer to the red end of the spectrum in the animation would just be where the stresses are the most concentrated, and any colors closer to the blue end of the spectrum would be the areas where the stresses would be least concentrated. And luckily and fortunately, through our validation we can conclude that the bike will definitely not fall apart when we're riding it and should be able to hold up reliably. So I'll hand it off over to Jared to talk more about how we plan on auto-generating bike frames to custom fit any person and any body size.
Sorry, I guess the wrong screen is being shared now. Okay, can you see the presentation now?
Yep.
Okay, so hi, thanks Johnson. I'm Jared Elliot and I'm in 2A Mechanical, and I'll be talking about the adaptive design process. So basically what that is being able to take in user inputs to create a specific model for a project. So after creating the general design for the bicycle frame, our next logical step was to make the key design elements user adjustable to ensure the end product is fully optimized. To achieve this, we created programs to intelligently automate our design. So we needed to take in specific user inputs, write algorithms to create the model, and then hopefully our goal was to create a smart design process that can take in information from a test or simulation of a design, and with preset parameters incorporate that into our future designs. The first step we took towards this was to create a table. So this has simple geometry, and in this video it takes in the length, width, and height and makes a custom table. The following adaptive design program can then be verified using the digital twin method mentioned earlier, where it can be analyzed for structural and fatigue performance relative to a set of requirements. And now, with the fundamentals we learn from the table, something of a greater complexity can be achieved using the Industry 4.0 ideas. With the bikes, the first step would be to take the general user anatomy measurement, leg length, arm length, and height, and weight, to get a model that is scaled to a specific person. To take this further, looking at more complex user inputs like the force on the pedals that could help determine other design parameters like gear ratios to maximize efficiency. Incorporating these algorithms and automating the process would also increase the speed of production and increase the quality of the product being made. Other things that we've also worked on is some artwork. So we've created braids, and it can also be expanded to, let's say, optimize PCB heat transfer. That's the end of the presentation that we have today. If there's any questions,